Hi, welcome to Chapter 3. Let me get the slideshow started. I can't start it and then hit go because ScreenFlow software won't let me do that. So here is part 2 of Chapter 3, where we go more in depth to least squares regression than you have probably ever gone before. I did put the calculator instructions in the 3.1 video to introduce you to it, and we will not go over that again in this video. But let's look at what we need to know about this process and why it's called least squares regression, and what the goal of the method is trying to do. And be grateful you don't have to do this by hand. Okay, so here is a typical example of a trend line or a regression line or the line of best fit or the least squares regression line, or there's lots of names for it, okay? We're calling it the least squares regression line, or LSRL, if you would like an abbreviation for your notes, because that indicates the exact method that was used to find this line, okay? So our scenario here is miles driven, and this is on cars, or passenger vehicles anyway, versus the price in dollars. So without even seeing data, I hope that you would think about the fact that the more miles that you have put on your car, the less you're going to be able to resell it for when the time comes to get a new car. So we see a negatively sloped regression line here. So when one variable goes up, the other goes down. They change in opposite directions. And so that would be expected. And I want you to think about the cause and effect relationship here to make sure we're comfortable with what variable we chose for X and what variable we chose for Y. And I think you'll agree that this makes sense, that the miles driven on your car is not something that you really control all that much. Yes, you do drive your car and you decide, how far a commute you're willing to do to work and things like that. But it's not like you said, I want my car to have this many miles on it when I go to sell it. You can try and plan ahead for that. But generally speaking, when you choose a variable for the x-axis, that is the number that is, in your opinion, driving the changes in the response variable, the whole idea of explanatory variable versus response variable. And so it makes more sense to put miles driven on the x-axis because first we drive the car and then we sell it. I think that's probably the simplest explanation. It has to do with what comes first. A can't cause B if A did not precede B, unless you just are a big Doctor Who fan, okay? So make sure that your choices for X and Y coordinates make sense for causality. And again, we're not trying to prove causality with a regression procedure. We will get to that in Chapter 4, when can you prove causality. However, we're taking baby steps toward it all the time. So this is a little formula that is included in the formulas. Let me pull that up here. I want you to take a peek at the formula sheet that you're allowed to use for this unit test and for the AP exam, and take note what's on it. So we're branching out of this formula, which is from Chapter 1, and notice there are no Chapter 2 formulas because the main use of this document for Chapter 2 was way down here for Table A, okay? That was 4 pages it takes to put Table A in here because they formatted it with huge margins. They could have made this document considerably shorter with larger margin or smaller margins, but oh well. So we do have some Chapter 3 formulas here. So here is our y hat equals a plus bx. That is on that slide I just had up, and I'll go back in a moment. You're going to see, and actually this one right here was from 3.1. That's our formula for our r value, which you will never have to do by hand on an AP exam. But for some reason, they've given you the formula. Here is a basic standard deviation formula. So they're going all the way across. That's Chapter 1. There were no formulas for Chapter 2, so now we go all the way across. These are Chapter 3 right here. And that will conclude our descriptive statistics formulas. The y bar and the x bar are the average of the y values for the xy data, and the average or the mean of the x values. So little formula down here. So know that you don't ever have to memorize these, okay? Now B stands for slope, and you may have to calculate slope by hand, but they're going to give you the standard deviation of the data or the actual data itself. Typically, an AP exam will give you S sub y and S sub x in the interest of time, because they typically only use these formulas in multiple choice questions. Okay? Just little AP exam tips you're not going to get out of your book. Alrighty, so we introduced this formula here. Y hat is a predicted value that the regression equation allows you to plug in x values and to predict y values for the input. So y hat is how you read it. Predicted value, B is the slope, A is the y-intercept. This particular equation goes along with the linear regression model in the calculator if you choose number 8 on the calculate menu. If you choose number 4, it says B plus AX or AX plus B, and A is slope and B is y-intercept. And that's fine as long as you don't confuse yourself. However, I suggest you use, under the calculate menu in statistics, use model number 8, and the variables in your formulas will be the same numbers as the variables in your problems and on your calculator. Best way to go. Just avoid the linear regression model that swaps A and B. Okay? Just less confusion. So mathematically, this is not complicated mathematics, simple linear equations, where the way to write them best is to model this. Please do not put x and y if you don't have to, because down below that you're going to have to say x is miles driven and y is predicted price. And why require, why make it so that you have to put that when you could just put it in the equation itself? So I'm going to train you to put words in the equation rather than x and y, because it'll save you rewriting it down below. So you are identifying miles driven as the input and 0.1629 as the slope, or negative 0.1629 as the slope, by inserting it in the equation here. And not introducing x and y when you don't need to as variables just saves time. So here we come to the most important word on this screen is the word interpret. Interpret means there's some pretty standard wording that you can memorize and use, and just put in the relevant context details and numbers, but use the same fill-in-the-blank kind of sentence to interpret a slope, okay? So let's look at what they did here as our example and maybe try and take note of some stock wording you can use. So the slope B equals negative 1.629. I would use 3 or 4 decimal places always, unless it just doesn't make sense with the type of data you're using. This makes sense because when you convert that, which is dollars, to cents, you get a couple decimal places. I know we don't work in hundredths of a penny, but when you round, you lose a lot of data. So don't round. Don't be anxious to round and make numbers super, super short. All right. In this case, I think 3 decimal places is too little. Okay. So the slope tells us that the price of a used Ford F-150 is predicted to go down by $0.1629 or 16.29 cents for each additional mile that the truck has been driven. This is perfect, okay? So our stock wording for slope tells us that the slope number is how much the y variable is going to change for a 1 unit change in the x variable. I'm going to repeat that again. The slope is how much the y variable will change, the predicted y variable, for a change of 1 unit in the x variable. Now, you don't say y variable and x variable in your sentence, you put the context in. So in this case, the y variable was the price of a used Ford, and the x variable is the number of miles driven. So please put the words number of miles driven and price of a used Ford instead of x and y, and you will have inserted the proper context into your question. Okay. The interpretation of the y-intercept is not asked very commonly, but sometimes. And I did discuss in the last video that sometimes the y-intercept doesn't make sense. But let's look at this case. The y-intercept A equals 38,257 is the predicted price of a Ford F-150 that has been driven 0 miles. Okay, well that makes sense. We didn't come up with some strange negative number that doesn't have any basis in reality. And like I said last time, just because your y-intercept doesn't make sense doesn't mean the regression line has no value for a prediction. It's just happy and nice when it does. Okay. Interpreting the y-intercept is not as common. Interpreting slope, you can bet it's going to be on every AP exam you ever see. But interpreting y-intercept, you could use the stock wording, and then if the number doesn't make sense, you could indicate that this doesn't make sense in a realistic situation. But in this case, where it does make sense, explaining that that would be the price of a new Ford would be a very valuable interpretation. So the word interpret is usually some set of very common wording that you can fill in the blank with the context and the proper number. All right. So yes, using the equation to come up with a predicted value is a matter of plugging in a value for miles driven and crunching the numbers and coming out with a predicted price. Reading it off the equation, off the graph, hard to do with any amount of precision, so always show your work. You want to show plugging in that number. They asked for the value of the car if it had been driven 100,000 miles, so you write the equation with the hat over the word price, because this equation is giving us a predicted value, not an observed value. And plug in your input and then show the price numbers crunched. So a Ford F-150 with 100,000 miles on it would cost, the price to sell it would, you'd be perhaps able to get $21,967 for it. So interpreting that answer is also good, because notice there's no dollar sign on that answer. They did put the word dollars, but if you want to be that student that always gets rounded up, you should put a sentence for an answer. All right. Extrapolation, just a warning that the predictive value of a least squares regression line goes down as you get farther outside the observed x values. So in this last, let's see, pull this up. If I'm going to say have a car that I've driven 200,000 miles, this line is going to have a very poor predictive value. If I have a car, well, see, it's always, or it already goes to 0. So on the left end, you can't have negative miles driven. So the left end is great for prediction. But if you extend past this last observation that's above 140,000, any length at all, really, the predictive value of the model is going to be less useful. And then, of course, this line is going to cross the x-axis somewhere and imply that if you drive a car a long, long way, that someone's going to have, or that you're going to have to pay someone to take a used car, and that just isn't the case, unless you're just paying somebody to tow off a hunk of rusted junk. So once that line crosses the x-axis, there's no practical value in its predictions, especially for negative slopes. But for positive slopes, things don't go to infinity always. That's not always practical in these real-life situations. So make sure that you're not extrapolating. The AP exam people do not like that. Okay. A residual. So this is probably the most descriptive picture in the whole section. It helps you understand what the least squares regression line is. It's one of two. They've drawn a vertical line from the actual observed values to the least squares regression line. And so you can see how far off each prediction is, either below or above numbers that overpredict, or numbers that are underpredicted by the line. So let's look at this number right here. This really long black line here indicates that this real life value is way underestimated by the line. Okay, and down here we've got a value that's a little overestimated by the line. So each prediction is off a little, and even this one isn't perfect, but it's the best one out there. This one's pretty good. This one's pretty good. The ones with a tiny little vertical line have very closely approximated values that line is helping predict those values really closely. So you don't draw those lines in when you do a scatter plot and superimpose the line of best fit over it. But this is a good description to help you understand residuals. So for this data point up here I pointed to, a residual value is how far off you are, and it is a signed number. What does it mean to have a negative residual value? What does it mean to have a positive residual value? Well, let's go over here. A residual is observed minus predicted. So if this number is positive, that means the observed value was actually higher than the predicted value. That would be all of these dots above the line. Those would have positive residuals. That makes sense. Upward is positive. So down here, the observed value is below the predicted value. So the residuals would be negative for the numbers underneath the line. That makes sense. So residuals can be negative. And rather than simply add up all the residuals and have some of the positive errors cancel out some of the negative errors, they square these numbers. So this is the second most valuable plot on the right here for helping you understand a least squares regression line. So we take each residual and we square it. And so you can see the square represents an area, and it turns every residual, so a residual squared, is turned into a positive number so that errors in one direction don't cancel out errors in another direction. And that then is used to help predict this line in a process that you do not have to be responsible for doing by hand. Hallelujah. All right. So here's the stated goal of the least squares regression line procedure. It makes the sum of the squared residuals as small as possible. So a calculator, a computer of any kind, has the capacity to do all those millions and millions of calculations to figure out which line is going to fit this best. And having not ever written a program that teaches a computer to do this, I know there's an infinite number of lines, and the computer clearly doesn't work forever to figure this out. So there have got to be limitations and guidelines that the computer is told how many times it has to check, or there's a range of values that it has to check some number from one end of that range to the other, but there's got to be a way for it to know when it's done and it has found the best line. So that might be, anybody that's into computer programming, that might be a question that you'd be better able to answer, or much more likely to be able to predict how a computer program would know when to stop looking. Okay, so we use an R value to talk about the strength of a linear relationship, and we will talk about R squared, but right now we're going to look at yet another way to evaluate how good a line that we come up with, how good is it going to be at predicting values. So a residual plot like this one has some similarities with the original scatter plot. Notice the x-axis is labeled the same, and the y-axis is in dollars, but it's just residual. So each of these points has a corresponding point over here. We take the observed value of y, subtract the predicted value of y, and call that the residual, and put the residual with the same x-coordinate, the residual, so this is a positive residual, and this one has a negative residual. So this one is under-predicted, and this one's over-predicted. Okay. And so what we're looking for in this plot to tell us whether this line of best fit is a good fit or not is we're looking for the residuals to be randomly scattered. We don't want patterns. Patterns would say that this line is systematically going wrong, or being overestimated or underestimated, or both. And as long as we have a general random scattering of residuals, then that is visual evidence that this line of best fit is a good fit, is a good predictor of values for this situation. So here are patterns in residual plots, and you can imagine what this means. If the lower data points on the x-axis continue to get closer to the actual value, okay, so they're way off down here and they're getting smaller, and then as you go past the exact right prediction, then they're moving farther away in the other direction, and then they come back down. This is not the pattern. This pattern indicates that a straight line is not a good model for the data that you're working with. So remember, these are just residual plots. They're not the original scatter plots. But these patterns would tell you that this data is not particularly linear, because if I were to erase this dot, you could still predict where it would be. That's not good. So being able to predict the errors means that there's a pattern in the scatter plot that is not a straight line. All right. So there is a statistic that is calculated. Most of the time you're given this number. This number is not on your formula sheet for the standard formula sheet you're given for your AP test, but it looks very much like a standard deviation calculation. Instead of being y minus y bar, it's y minus y hat. And instead of n minus 1, it's n minus 2. And I know that might be bugging people by now, instead of just dividing by n to get the mean, okay, under that radical. In Chapter 7, we will hash it out a little better, maybe not perfectly, but we'll talk about why we're not dividing by just plain n when a standard deviation is an average distance from the mean. It is an average of sorts. I like the word typical better, though, because it's not a pure average, or we would be dividing by n. So S, in this case, called the standard deviation of the residual, it also has other names, as we'll see in a little bit, is the typical prediction error. All right, so it's nice to know how far we are off typically, or on average is another phrase you could use for that. So we talked about r in 3.1. Now we're going to talk about r squared. And it is literally just the r value squared. And here is a different formula for r squared than we saw for r. We could compare the two. If we go back to that and take a peek here, you see how we have x minus x bar, y minus y bar on top. So these are deviations from the mean. And then they're being divided by the standard deviation of each of the variables. There is a summation, so we're multiplying these standard deviations, or the number of standard deviations from the mean here and here. We're summing that up, then we're dividing by n minus 1. It's close. It's not the exact same formula. But the residuals, that's y minus y hat, not y minus y bar, quantity squared. Down here, y minus y bar and quantity squared, and all of them added up, subtracted from 1. R squared is a positive number, and it is always less than 1, indicating that it is a percentage. R squared is a percentage. R is not a percentage. So let's make sure we don't confuse the names. Plain old R from section 3.1 is your correlation coefficient, CC. R squared is called the coefficient of determination. It also has other terms, but they really only use this one in this class. So if you have R, you can figure out R squared and vice versa, but they mean different things, okay? Now let's look at the description down here. R squared tells us how much better the LSRL does at predicting the values of Y than simply guessing the mean Y value for each value. Okay, it's a percentage, and the description that I like, if you want some standard wording, it is in the book, I believe. It is going to tell you R squared gives you the percentage of, or it, make sure I get the wording good. I'm not looking at it, I'm doing it from memory. Is the percent, it explains how well the model accounts for the variation in the observed Y values. So it's a percentage rating of how well the least squares regression line accounts for the change in the actual Y values. There's your wording, okay? Now, don't say Y values, put the context in, okay? So, want to look at, see, this is a specific question from the chapter, comparing the number of points per game that football teams have scored and comparing it to the number of wins they had in a season. And so when you see a scatter plot with the line, the least squares regression line drawn, superimposed over the data, and the residual plot, they have some similarities. It's almost like we just took the least squares regression line and evened it out, but that's not what happened, because if we did that, then 0 should be right here, and it's not. And remember, this is not the same label as the y-axis over here. This is the same units, numbers of game wins, still numbers of games won, but the residual is how far off our observed value is from the predicted value. Okay, so observed minus predicted. And there's a good little memory trick to get the order so you don't do the wrong order of subtraction. Observed minus predicted, O is for observed, P for predicted. In the alphabet, O comes before P. So observed minus predicted is the proper order to calculate a residual in, so you get your sign, positive or negative, correct when you calculate this. So you draw your dots on the proper side of the line. Now, I don't know of very many questions on the AP exam, if it's ever happened, that you had to draw your own. You might have to draw one after putting data into a calculator and having it draw your residual plot for you. And I want to go into the calculator and again, make sure your diagnostics are on for statistics. And I believe I still have my data in here from an example in the last section. So we're going to do the residual plot for this one. So originally, under statistical plot, I think I have everything in here still. See, we did the scatter plot last time with list 1 as our x-coordinate and list 2 as our y-coordinate. And I believe this was a question comparing the sodium content in milligrams of a McDonald's, of different types of salads at McDonald's, comparing it with the fat grams, okay? And so if we want to do a residual plot here, we're going to have to go to the list, okay? And the book has this walkthrough. We're going to edit the lists, and so we're going to arrow over and up, and we're going to tell this. Now, we need observed minus predicted, okay? Observed is L2, and predicted is going to be, let's see, I'll give you a page number to go back over this. And maybe I will skip talking about this in the video just to keep it from being so long. But this starts on 175, and it has you add a list to do the residuals, for the computer to calculate the residuals for you, so that you don't have to do all that by hand, and come up with a new scatter plot that is the residual plot. And so that's going to be pages 175 and 176. So I think I'm going to leave that out of the video, and you can ask me questions at the sync session about it if you're having trouble doing it, just in the interest of keeping this video a good length, okay? PowerPoint. Okay, so that'll save us a little time, but that's an important skill to be able to do. And the much more common thing that you'll have to do is use your least squares regression line equation to figure out how far off a value prediction is for a single point. So here we look at a particular team. They scored 30.1 points per game on average, and if we were to plug that into the least squares regression line, it predicts they would have 9.4 wins. Please do not round that to 9, down to 9, or up to 10, because it's just theoretical. Okay, I know you can't win 0.4 of a game, but it does not require you to round, because you then lose information. It's not as small as 9, so we don't want to round it down to 9. All right, our residual is our actual 11 wins minus the predicted value, so we were off by 1.6 wins. And now we go to look at the standard deviation, okay? Oh, that's on the next screen. That was good, me hitting that by accident. They actually won 1.6 more games than we expected to based on the model. All right, and so we want to be able to look at a residual plot and tell if a linear model is appropriate, and that is based on us desiring a random scattering of residual points. Now, the word interpret is here again, okay? And so S is the standard error or the standard deviation of the residuals, and according to the formula, it says, okay, and here's your interpretation, we will typically be off predictions about the number of wins a team will have based on their average points per game by about 1.24 wins. And we were off by 1.6, so that standard deviation is pretty close for the one value that we observed. Then here's our interpretation of R squared, a percentage. 88% of the variation in the number of wins, the y-coordinate, is accounted for by the linear model relating wins to points per game. That's an excellent little bit of stock wording there. Just put blanks in for the context of what X and Y are, and you can use that wording over and over again. I like to see you put it as a percentage because it helps me understand that you know what R squared means. Okay. Throughout the book, you'll be asked to interpret computer printouts, and sometimes they're in slightly different formats, but they're all pretty straightforward. Some things that you'll see that we're not going to use, we're never going to use R squared adjusted. Just know that now. And while we will use these 6 numbers eventually, we won't in this chapter. So they have circled all the relevant things so far. Sometimes they say y-intercept here, sometimes they say constant, but they're talking about the predictor in the equation, in the y-hat equation. So the constant would be the y-intercept, the miles driven, we know that's our x value. So they'll name the x value. And the predictor, notice how it says coefficient. So this is the coefficient of miles driven, which would be the slope value. This would be our constant value, which is the y-intercept. And so here they do all the number crunching for you. If you needed plain old r, you could take the square root. But since r is not a percentage, remember r varies in between -1 to +1. It's not a percentage, so please do not take the square root of 66.4 to get r. Please convert it to 0.664 and then take your square root, and then you'll have a proper r value if you need to figure out r from r squared. Why they don't list it separately in most of these printouts, I do not know. But they did nicely hand you standard deviation of the residuals. You will almost never have to calculate that for yourself other than a single point here and there. Here's another way. This is software called JMP. I think the previous one was called Minitab. Here's JMP software. See, it says R square. Remember, we don't use R square adjusted. Here, they're pointing out S, but here it's called the root mean square error. Well, it is a square root in the formula, and there's a mean of sorts in the formula. So there's an alternate name for standard deviation of the residuals. And down here, the y-intercept and the slope value says intercept. So that's nice instead of the word constant. But it names the x-axis, and this, of course, would be the coefficient, or the slope in this case. So just get used to reading the different printouts. Now, possibly the easiest question you will encounter in multiple choice, and there is often one of these on every AP exam, is one where they give you the standard deviation of the x-coordinates, the standard deviation of the y-coordinates, and the r value, and ask you, and the mean, x bar and y bar, and ask you to come up with the least squares regression line. So you have to figure out A and B with these formulas and plug them into the line. Possibly the easiest question in the whole class, okay? Just plug your data points into your calculator, right, if they don't just hand you these to begin with, and I've seen that, where they said SY is, SX is, Y bar is, X bar is, and R is, and they have to give you all 5 values for you to do the question, and a lot of times they do. So just know that that question is not some hidden meaning that's hard, but it tricks you into thinking it's easy. It truly is easy. Okay, I know sometimes people freak out when something's easy because it's not supposed to be easy or something. All right, here, this slide is telling you the importance of not mixing up the explanatory and response variable. Kind of talked about it already, that the price of a car doesn't determine how many miles it was driven. It's the other way around. All right, I like this slide. This slide is very instructive. I would like you to pause maybe and guess what the correlation coefficient, these are all scatter plots. These are not residual plots. These are scatter plots. And I want you to notice the scales on each plot is the exact same. And I want you to guess the R value. So I encouraged you to play games with guessing R values. And so here's your game. So pause right now and decide what you think the R values are here. Okay. Now, if you're not going to pause, you're just going to see it. But here we go. There's the R value for every single one of them. And clearly, we are not going to use a linear model for this, looks like, parabolic data up here. It could be sinusoidal. I don't know. I'd have to check it out. But we're not going to do those types of models in this class. We only do linear regression in this class. So, and in this chapter, we don't even consider other things. So we're just going to say that this is not a set of data we would use a linear model for. This one is just weird, okay? It's got the same R value, but they basically played with this until they put this point far enough out there for it to have the R value and demonstrate how this set of points can have the same R value as the rest. Now, a perfectly vertical line is not a good predictor if a situation doesn't come out the same every time. So clearly we had one weird outlier in this data set, which allowed this R value to still be fairly high. So because this data is pretty linear, it's just, how is this possible? That might be, as a statistician, a reason to look in to see if when this value was measured, if you screwed up or not, okay? But a constant value here of, you're putting in the same value every time and getting out different stuff every time, that's not a function. You can't predict stuff. So even though this is not even a function, if you just look at this part, it's kind of weird that you could have data like that. So sometimes you'll see bands like this. There's a whole bunch of vertical ones here and a whole bunch of vertical ones here and a whole bunch of vertical ones here. I've seen that before, but at least it's varying with different x values being put in. But this is just confusing how you could even use this with a linear regression model. These are a little bit more understandable. This one's fine. This one just has one weird outlier that should draw your attention and beg some kind of inspection at least. But it's just strange all these came out with the same R value. All right. By the way, they all came out with the same regression model too. So the point of this slide is to tell you that we're not going to use a linear model when the data is not linear. And I know these aren't in a straight line, but this is a predictive value that at least follows the general path and trend of the data, whereas we know clearly this is going to end up going back down from the pattern, and a straight line is not appropriate here. Now, I wish I had this line drawn over this graph to see what this does, because I don't see 0, 0 on here, so it's hard to make a graph here look right. I don't even see the number 3, so graphing this would not be the easiest since the scales are different on the two axes, but that's just weird that all these come up with the same equation as well. It's just pointing out we're not going to use linear regression for this one, and we probably won't use it for this one. Okay. All right. So this is a sample question from the book talking about a test that is given to young children with regard to their speech ability. And it's to discuss the effect of outliers on a regression line. A regression line is yanked all over the place by outliers. It is not even a little resistant. So we have these two outcomes here. And this is the least squares regression line that results from this whole data set, even the two outlying points. And we want to see what effect outliers have on this line. So up here, all 19 children, that is the green line, okay? That is the line from the previous slide. If we were to drop child 19, if we were to drop child 19 up here, then this would be the new line. Now, that improves the R value. So remember, closer to -1 or +1 we get, the better. The slope only changes a little in that second decimal place. The y-intercept is very close. So dropping this point that's off, that is an outlier in the y direction, greatly improves our regression line. What does dropping this child do? So if we put 19 back in and take 18 out, we get this blue line. Okay, actually I didn't even mention the red line. So the red line is if we drop child 19 and get this much nicer equation. See, the effect of including child 19 is that this red line gets pulled up a little bit. Okay, so that vertically outlying point does have a small effect on the slope of the line. What about the horizontally outlying point? If we drop that one and keep child 19, we get this terrible R score. So this point over here that was outlying in the x direction had a massive change on this equation. Look at the difference in slope. 1.1 versus, this is 0.4 difference in slope roughly. Not exactly, but roughly. And the y-intercept's not horribly off. That slope is way off. So this child 18, when we drop it, the green line pops way up here to the blue line. So something to walk away from this sample problem with is that a horizontally outlying point has a much bigger effect on slope than a vertically outlying point. The child 19 point vertically, dropping it improved things greatly. So what we know is a horizontally outlying point pulls the line toward it. When we have this blue line without child 18 and put child 18 back in, it goes way down here. So the horizontally outlying point has a much greater effect on the line than the vertically outlying point. Okay, although dropping 19 made a much better R score. So of the three, I would rather have this line, including child 18, but not including child 19 in the end. So it's not like you can say, oh, this direction is bad and that direction is good. You do have to see, but it's a kind of question they would ask you: if this point was dropped, what would be the effect? And they'll do that a lot. They won't show you the line. They'll just ask you to describe it. So know that the horizontally outlying point has a much bigger effect on slope. The vertically outlying point gave us when we dropped it, gave us a better R value and overall a better model. See, without the point out here for child 18, it's hard to predict which way this line is going to go between this point up here and this one down here. So this child 18 gives the slope some real direction, okay? And so you need to be able to interpret that kind of situation. By the way, the book did not provide the picture if we dropped both outlying points, and it was really making me curious. So I did this on Excel, and we have a negative 1.05 slope, and this horrible R squared value, 0.27. You want as close to 1 as you can get. And let's see, the square root of 0.27 is also a terrible R value, not R squared. It's a 0.52. It's just a horrible R value. So if we dropped both outliers, then we get a terrible line. Look at this. Positive 0.52 R value. Actually, it would have been negative because it was downward sloping. It's almost the worst. So dropping child 18 makes it the worst, but dropping them both is terrible. So it's not that you want to drop outliers. You just want to see what effect they had on the data, okay? And in some cases, it's unethical to drop outliers. All right, so this is a summary of what we talked about with points that are influential in affecting a least squares regression line. Okay, that's all I have for you. Thanks so much.